Okay, so this is a typical young double slit question. Okay, so monochromatic light source emits light of wavelength lambda. S1 and S2 are both at a distance of 0.15 mm that's written here. So that means that the distance between the two slits is 0.3 mm. Okay, so that's first thing we can see. So we need to take note of this. Then next, okay, let me just make it clearer. Okay, 0.30 mm. Okay, so next part is O is the position on the screen from S1 and S2, and there's an interference pattern of bright and dark fringes. So this one is the third order minimum. Okay, third order. Okay, so it's not it's after the first and the second is the third one. Okay, so and it's a minimum. So first thing, state the three conditions necessary for a well-defined interference pattern. A is memory work. So this is pretty straightforward. Okay, so the first condition that you need, okay, let me just make this bigger and change the color. The first condition that you need is that they are this is they are okay, so the two waves must be coherent. Okay, so the two waves causing the uh let me see, yeah, the two waves resulting in the interference pattern. Okay, let me drag this. In the interference pattern must be coherent. Okay, coherent just means that there's a constant phase difference. Okay, which is what the young double slit is doing with their single slit. Okay, number two. So you also need to know that their amplitudes, the amplitudes of the two waves, are approximately equal. And number three, because in this case it's a light source, it's an EM wave, so it's a transverse wave. Okay, so the third condition is that the waves must be polarized or polarized in the same plane. Okay, so it's always these three. Next, write down the relationship between S1Y and S2Y. Okay, let me just put A here and B on the right side. So easily, this is the third order minimum. Okay, and these two are in phase because of this single slit. So they have two sources in phase with constant phase difference. So the third order minimum just means that, okay, first order is half lambda, then 1.5 lambda, then 2.5 lambda, or 5/2 lambda. So this is a third order minimum. Okay, so that means that S2, you see that it's nearer to S1Y. So S2Y minus S1Y must be equals to 5/2 lambda. Okay, so this is the relationship. And then part two, you are supposed to then find the angle theta. Now, for some students, it may be very tempted to use the diffraction grating formula, d sine theta equals n lambda, but don't. Okay, because this is a double slit question. So it's not a diffraction grating question. The formulas are different. They are because they are derived with different conditions. Okay, so what we need here is that x, we know that x equals to lambda d over a. Okay, this is d. This length here is d. But here, what is the distance? Okay, so if you recall for young double slit, okay, so let's say this is a central fringe, 1, 2, 3. Okay, this is a third order minimum. So what happens here is that bright to bright is x, bright to bright is x, bright to dark is x over 2. So the distance here, or the distance here, is going to be 5x over 2, or 2.5x. Okay, x plus x over 2 is a third order minimum. This is the first, this is the second, this is the third. Okay, so we need to find, in other words, this divide by this, or 5x over 2 divided by d. We need to find this value. Then we set this to tangent theta. So that is the objective. We need 5x over 2 over d. Okay, or 5x over 2d. Okay, so you can actually write this down somewhere inside as part of your working as well. Okay, so we know that tangent theta also, you can write also tangent theta equals to 5x over 2 divided by d. Is understood. Okay. So you get 5x over 2d. Now, from the first equation here, x over d is equals to lambda over a. And now you have lambda 400 nano. You have d, no, you have d. You have a, which is 0.3 mm. Okay. So you can actually find what is x over d. Just press on your calculator. Okay. So 400 nano divided by 0.3 mm. You get 0.001333. Okay, a lot of threes here. So now we know that tangent theta, which is equals to 5x over 2d, is actually 5 over 2 times this. Okay, so you multiply by 5 over 2, you get 0.0 0.0033333. Okay, so now you can find your angle. So tangent inverse it, you will get about 0.19 degrees. Okay, it is indeed going to be very small. Okay, because Young double slit, you can see that all the fringes are generally quite close to each other. Okay, so small should be correct. Okay, next one, part C. Discuss the changes to the interference pattern if the 400 nanometer light source is replaced with a laser of lambda 650 nano. Okay, so C part 1. We know that x equals to lambda d over a, right? Okay, let me shift this a little bit. So you can see that the larger the lambda, which is what is happening here, 650 is larger than 400. The larger the lambda, the larger the fringe separation. So what you'll get here is that the fringe separation, the fringes, okay, will be further apart. Or the fringes, or the bright fringes, the fringes will be further apart. Okay, or the fringe separation will be larger. Okay, so they will be further apart. They spread over further. So what does that mean also? The maximum or the brightness will also be reduced. Okay, why I need 2? Because you can see here 2 marks, we need 2 points. Why will the brightness be reduced? Okay, this one is from your single slit diffraction. Okay, so basically it's spread over a larger space, larger area. So because of that, your intensity will drop. Okay. Now, number 2, white light. White light consists of different frequencies. Okay. So, okay, let me see. C part 1, I think you may also need to. The other way you could probably say is to okay, let me I think we just remove this one. Okay, make a mistake here. Okay, probably I will say that this one is 1 mark, this one is 1 mark. Okay, I'm not so sure about the brightness, although it may be, but we don't need it. Okay, because the question talks about discuss, so we can consider that we are just giving the reason why, because here is 3 marks. That's why I thought of it. Okay, we need to give the reasons why. Okay, so since x is proportional to lambda, you probably use that as the first one. X proportional to lambda, therefore the fringes will be further apart. Okay, so we reduce one. Okay, so the next one, okay, let me just put it here. So white light, so we need to explain for white light as well. Okay, so we can say that white light consists of a range of frequencies. White light consists of a range of frequencies, okay, which is, yeah, red, orange, yellow, green, blue, indigo, violet. So because of that, each individual frequency is a different lambda, okay? And hence a range of wavelengths. As such, the different colors of lights, of white light, will have different fringe separation. Okay, let me just move this to the center. Okay, so they will have, okay, so this is part C, part 2 here. So as such, they will have different, they will have a different, they will have different fringe separation, okay? So what we'll see, so I will say that this is probably 1 mark, then this is probably 1 mark, and then the last one is describe what you'll see. So the fringes, okay, or the interference pattern, or what we'll see is a whole white light spectrum, okay? So as we'll see a white light spectrum is seen on the different orders of the interference pattern. Okay, something to this effect.